So today I'm going to talk about queues. So queues, by the way, one of the most useful data structures. So this is part one of three of my talks. So today I'm going to talk about queues implementation, and next I'm going to talk.
Are you recording?
Yes, I'm recording. Okay, so here's the outline. I'm going. So we'll be going over what queues are, when and where they are used, and we'll also look at some complexity, time complexity, and memory complexity. What queues are and when. Of these queues, and an example involving queues. And lastly, we'll discuss the implementation details of enqueuing and dequeuing operations of the queues, and followed by some source code. By today, we're going to we're going to make a discussion about queues. So now the discussion. So, okay. So, now let's talk about what is a queue. So a queue is a linear data structure which models real-world queues. So it has two primary operations. They're named as enqueue and dequeue. Enqueue and dequeue. So below at the bottom of the slide, you can see a basic queue.
Yes, I can.
Okay, it works. Okay, so okay, are the slides changing now? It works. Everything works.
Yeah.
So every queue has a back and a front. Every queue has a back and a front. So we insert elements through the back of the queue and remove them from the front. So adding elements to the back, or we're adding and removing, is also known as enqueue and dequeue. But adding is known as enqueue, as we are, for example, entering the queue. We can imagine it as entering the queue, and dequeue is the same thing. As the removing elements from the queue, from the front of the queue. Okay. Now let's talk a little bit more about terminology. So some people says enqueue operation in different manners. So, for example, to put in other words, their terminology doesn't seem to be some consistent terminology for inserting or adding and removing elements from queues. So, enqueue operation, some people refer to enqueuing as adding or even offering elements to the queue. And the same thing for dequeuing or removing from the front of the queue. So that is sometimes known, dequeuing is sometimes called as pulling an element from a queue, and some people refer to as removing, but that causes some ambiguity. So does this person who said that we're removing, does he really we mean removing from the front of the queue, or specifically from the front specifically, or from the entire queue, from some specific element. So we want to remove some specific element in the middle or in the end, or specifically at the front. At the front, that is known as dequeue or pulling. So
Polling.
yeah, so when referring to removing, also usually in the sense of dequeuing, but to say specifically to say from the queue, the entire queue, I'm going to say that we're removing from the middle, for example, because otherwise that is pretty ambiguous. Okay, now let's look at an example of how this. So let's look at an example of how a queue works in some detail. So first, we have labeled the queue's front and the queue's ends. So we can say that we have a front pointer and a back pointer. So that is where so the front and back ends, that is where we will be dequeuing and enqueuing respectively to remove any confusion. Okay, so the first operation says to enqueue 12. So we're at 12 to the end of the queue. So we are adding this number, this element to the queue. We are enqueuing. And then the operation says dequeue. So we remove the first element from the queue. I think we can refer to top element from the queue. Okay, now we are popping it. We are polling it, for example. So dequeue again. Okay. Now we want to make a dequeue operation again. So this time we remove -1 from the queue. We're removing the front element, and that is -1 this time. So now let's enqueue 7. We want to enqueue 7, and we'll do that to the back of the queue. So we'll insert to the back of the queue. So that is what enqueue operation means. And we have a dequeue operation now. So we want to remove the front element. And the last operation is to enqueue. So we're just adding -6 to the end of the queue. We're adding negative to the end of the queue to, I think we can refer to the right side of the queue. Okay, so now we have looked at this list of instructions. And now that we know what a queue is and where does it now let's take a look at where, when, and where does this data structure used. So a classic example of a queue is to model an actual queue or a waiting line. We can say to model a waiting line, real world waiting line, such as in the movie theater or in the restaurant, for example, when people waiting to get served. For example, when someone waiting in the queue because all the how can we say all the cashiers? No. The
Cashiers.
yeah, cashier. Thank you. Yeah, all the cashiers are busy. They're serving other customers, and once one of them is freed, the next person, the next client, gets to order some food or buy the ticket. So that is the waiting line, the queue, and that is the representation, we can say, of the data structure, queue data structure. And there are also some other practical usages of these queues. So they're also really useful if you need to keep track of most recently added items. For example, we want to keep track of X most recently added elements. So we need to do is whenever the queue contains more than X elements, we're dequeuing the last elements. We're removing the last elements or dequeuing them. So we're leaving, in other words, we're leaving the most recent elements. Okay, now queues are also used in server request management and some web service request management. So, for example, if some manager of server wants to build a system that is known as first come, first serve. So, let's suppose, or let's imagine that the server is waiting for requests from people to use some website and at any given moment it can serve five people simultaneously, but no more. So if 12 people come in one after other in a short period of time, at one moment we can say we may not be able to finish processing all the requests at once, and new ones come. So while during this process, we are able to so we're okay. We can say it this way: while we process the request of 5 people, other 7 people in our case I guess are waiting in the queue. Are just remaining in the queue, waiting to be served, and afterwards, as the current 5 people are processed, their requests are processed, we can now serve the other. So we're simply dequeuing the next elements until the queue is empty, and that means we have served every user of our site, for example, or web page. So everyone is served. And also a bit advanced application of this data structure is when we're performing a breadth first search traversal of a graph, and we're going to see an example of this a bit further, I think, in the next video, in the next talk. Yeah, so that is in the next talk. I'm going to talk about,
In the next talk.
yeah, in the next talk. So now let's look at the complexity analysis. So now we have looked at where and when they are used. We have the basic comprehension of their usage examples, and we'll, for example, now want to know their time complexity. So, by the way, as we have seen, it's pretty obvious that enqueue and dequeue operations are constant time, because so it's pretty obvious because with this data structure we are enqueuing and dequeuing at a constant time. So with this queue, okay, and a constant rate. Thank you. So peaking means so the other data structure, the other now operation is known as peaking. So that is the same as dequeuing operation, but we're not removing. So we want to know the value at the front of the queue without removing it. So this is also constant time as the dequeue operation. However, checking if our queue contains some element takes a later time, because we need, in a worst case, we'll need to scan the whole queue if it contains the element. For example, this worst case, if this queue does not contain this element, or this element would be at the very end of our queue. In this case, it'll take the linear time, the O of n time, or rate. So the removal from the, not from the and from the front of our queue, but from some element takes the linear time, because due to the fact that we will need to look through every element, we'll need to process every element, to scan every element before we will before we'll remove some element, and checking if this is empty, if some queue is empty, takes the linear the constant time of one time. So that is pretty easy. If we can pick the element, that would be that means that our queue is not empty. So, by the way, that's the end of today's talk. So that is about in some sense, introduction to queues. And next time I'm going to talk about enqueuing and dequeuing operations, implementation details, and some more examples, with an example of BFS. Okay, thank you.